At the end of the year, 2025, the inner solar space is preparing for what astronomers see very rarely. The appearance of a whole wave of giant comets, including the interstellar visitor Tri-I Atlas, simultaneously fills the surroundings of Earth. Forget routine astronomical events. This rich composition creates unique scientific opportunities and raises the stakes as strange jets and solar storms threaten to alter our understanding of the origins of these icy wanderers. Why are so many giants awakening right now? And what can they reveal or destroy by the end of the year? This is how the comet traffic jam of the century began. 4 giant comets in one season is not just rare, it's almost unprecedented. The inner solar space, usually a stage for lonely wanderers or random couples, suddenly became crowded. Astronomers around the world rushed to keep up with ongoing events. Professional observatories and amateur telescopes are under pressure as every clear night brings a new target and a new set of data. This is not an ordinary slow parade of icy guests. Instead, we witness a jam where each comet demands urgent attention and offers a fleeting chance to capture phenomena that may not repeat for decades. The composition is impressive. There is an interstellar traveler, Tri-I Atlas, whose hyperbolic trajectory passes through the solar system at a steep retrograde angle. Next to him are 3 bright comets, Lemmon, SWAN, and K1 Atlas, approaching their closest points to the Sun. Each of them follows its own trajectory, but they all fill the same space near Earth's orbit. This convergence forces astronomers to balance resources and time, as no one wants to miss subtle changes, emissions, or disruptions that can occur in just a few hours. The load on observations is colossal. Coordinated campaigns are taking place on different continents. International networks plan the timing of telescopes to catch every possible window. The stakes for science are high. Each comet acts as a probe, revealing how solar wind, magnetic fields, and solar eruptions shape their tails and streams. When so many comets are active simultaneously, the chance to compare their behavior under similar solar conditions is unique. It's not just about collecting beautiful images. These are live experiments in the field of dust plasma physics, chemistry, and the history of the solar system. For many researchers, this is a once-in-a-lifetime event. The sense of urgency is well-founded, as the window of opportunity will close quickly. Comets will fade, data will disperse, and the next time such a jam occurs, today's technologies and expertise may be unavailable. For now, the struggle is in full swing, and every observation matters. The calendar of this comet season resembles a list of rare events. The first event occurred on July 1, 2025, when the Atlas survey in Chile detected a new object, Tri-IIR Atlas, whose orbital trajectory indicated it came from beyond our solar system. His path to the Sun is steep and retrograde, with an inclination of about 175.1 degrees, indicating interstellar origin. For several months, Tri-I Atlas is rapidly moving towards the Sun. But on October 21st, he reaches the highest point of the connection, passing behind the Sun from the Earth's perspective and disappearing into the sunlight. In just 8 days, on October 29th, it reaches perihelion at a distance of approximately 1.36 astronomical units from the Sun. Observers will have to wait until the end of November or December for it to reappear, becoming visible to ground-based telescopes and with long exposure. Meanwhile, the comet C225R2, also known as the SWAN, has already made its closest approach. It reached perihelion on September 12th, coming within 0.5 of an astronomical unit from the Sun. Now it is fading and moving away, its window for easy observation closing. The focus now is on comet C25A, known as Lemmon. This comet approaches its perihelion on November 8th at a distance of 53 hundredths of an astronomical unit. The Lemmon is active and dynamic, with jet-like structures and spiral features that change within minutes. It is popular among both binocular users and in telescopic imaging campaigns. Its rapid evolution has made it the center of international observation, especially after the Tenerife campaign captured double spiral jets in October. Ahead, comet C225K1, also known as Atlas, is still moving towards us. Its perihelion is expected on December 31st at a distance of only 33 hundredths of an astronomical unit, the closest passage to the Sun among all 4 comets this season. The exact brightness and visibility are still being clarified as new data comes in, but its close approach has already included it in the observation lists for the late months. This schedule is not just a list of dates, each event is a unique opportunity. The geometry of their orbits, especially the steep interstellar path of the three comets, A Atlas, means that observation windows do not repeat. Each closest approach of the comet to the Sun marks a peak of activity, but also a narrow window for observation. For astronomers and astronomy enthusiasts, the coming months are already planned, and each night offers a new alignment, a new challenge, and an opportunity for discovery. The role of the Atlas survey in identifying both comets I Atlas and KO1 Atlas highlights the importance of wide-field sky monitoring in this era of comet traffic. The three comets I Atlas stand out against other comets in this busy season. Their trajectory is not just steep, it is hyperbolic with an eccentricity of more than 6 and an inclination of about 175 degrees. This path is a mathematical signature. The three comets I Atlas are not from anywhere here. She entered the solar system from interstellar space, crossing the planetary plane almost upside down, and then left again, never to return. For planetary scientists and dynamicists, this is a rare opportunity to study matter that has traveled millions, even billions of years between stars. The scientific value of the three comets, I-ward Atlas, lies in their chemistry and dynamic past. Observations from the Very Large Telescope, James Webb Space Telescope, and Hubble Space Telescope revealed an unstable composition, mainly consisting of carbon dioxide with the presence of water ice, carbon monoxide, cyanide, atomic nickel, and carbonyl sulfide. This composition is both familiar and alien. It shares features with the comets of the solar system but hints at subtle differences due to its origin far from our Sun. The emission rates recorded as the comet approaches perihelion show that carbon dioxide is the main driving factor, especially as the comet heats up. These measurements are not just a catalog of chemicals. These are hints about the conditions in which the comet was born and the processes that shaped its path through the galaxy. Dynamic modeling using high-precision astrometry related to the Gaia coordinate system allows researchers to trace the path of Comet 3I Atlas back through the Milky Way. Monte Carlo simulations with thousands of orbital clones suggest the probable origin of the comet from a thin disk of the galaxy, an area rich in metals and young stars. The speed and trajectory of the comet exclude local associations or recent stellar encounters. Instead, the evidence points to an outburst from a dense region rich in volatile substances, possibly around 100 million years ago. Each new data point, every night observation refines this story. For the scientific community, the three I Atlas are not just a guest. This is a messenger from another solar system, carrying information that cannot be found anywhere else in the sky. Solar activity is not just a backdrop for this season's comets. It is a constant force shaping what astronomers see from Earth. In recent weeks, a series of coronal mass ejections surged through the corridor between Venus and the trajectory of Comet 3 Atlas. These enormous eruptions of plasma and magnetic fields rushed outward, crossing areas where comets are currently located. When the KVM crosses the comet's position, the consequences can be immediate and dramatic. Ion tails may turn off, jets may swirl or brighten, and the entire appearance of the comet can change in just a few hours. To track these changes, researchers rely on a network of spacecraft and complex solar models. The ENL and WSA models, based on data from missions like SOEO and DSR, predict the timing and trajectory of solar storms. Real-time telemetry indicates when the spacecraft is likely to cross the comet's orbit, alerting both professionals and amateurs about possible abrupt changes. This is not speculation. Warnings from the International Asteroid Warning Network and NASA's meteorological bulletins have coincided with observed disturbances in comet tails, confirming a direct link between solar events and comet reactions. The latest coronal mass ejections are of particular interest. The comet is hidden behind the Sun from the view of Earth, but models show that these solar storms passed right through its presumed location. When the three comets, I in AT, reappear at the end of November or December, astronomers will search for evidence of these encounters, torn tails, altered jets, and other signs of solar interaction. The same applies to the comets Lemmon and K1Os. The changing face of each comet is not just the result of its own chemistry or orbit, but a record of the Sun's moods in real time, captured in plasma and dust. Understanding this sunny context is crucial for interpreting the rapid, sometimes astonishing changes that define this rare comet season. At the top of a mountain in Tenerife, a team of astronomers has recorded something unusual. Using high-speed photography, they tracked the inner cometary coma of Comet Lemmon as it released two steady jets named A and B, which spiraled and changed shape in real time. These jets did not simply drift or disappear. They pulsed and twisted, sometimes changing their appearance in less than 5 minutes. The movement of the jet reflected the rotation of the comet, revealing a core spinning on its axis and ejecting material in steady, repetitive bursts. The team created a map of the time and direction of each emission, discovering that the spiral patterns were not random. Rather, they corresponded to the expected behavior of a rotating body emitting gas and dust from fixed points on its surface. Spectroscopy added another level of detail. As the beams became brighter, the instruments recorded clear signatures of ionized molecules like CO+, H2O+, Cr2, and Cn, each leaving its own spectral imprint. The intensity of these lines fluctuated depending on the activity of the jet, showing that the emissions were not just dusty, but also rich in charged particles. The presence of CO ions and H2O in particular signaled intense solar chemistry, where ultraviolet light and solar wind tore electrons from escaping gases. These ions instantly react to changes in sunlight and magnetic fields, making the stream sensitive indicators of both the comet's internal state and its surroundings. High-speed filming during the Tenerife campaign proved essential. Minor changes would be invisible in single shots or slow reviews. Only by overlaying sequences and analyzing each frame could the team observe how the streams evolved, twisted, and sometimes faded. The result was a live recording of cometary activity, captured in the moment. A direct window into the physics of dust plasma, where gas, dust, and solar energy unite to create forms that are both beautiful and deeply informative. Data from Tenerife now serves as a benchmark, showing how much can be learned when observers are ready to capture the most fleeting moments of a comet. Comet C2025R2, known as SWAN, is now quietly retreating from the sun. Its brightness is fading, and the once prominent tail gradually disappears against the sky. For observers, SWAN is a starting point, a stable, predictable comet that offered a brief period of activity after perihelion, but now mainly serves as a basis for comparisons. However, even during its calm departure, the SWAN comet left behind mysteries. Images captured a distinct bifurcation in its tail, while some reports hint at possible fragmentation, challenging previous models of dust and gas ratios. These anomalies have sparked debates among theorists who are now revising their assumptions about how solar wind and the internal structures of comets interact with each other. Comet K 2025 K1, or Atlas, tells a completely different story. Her approach has nothing to do with the routine. The nearest perihelion for comets this season is only 33 hundredths of an astronomical unit from the Sun, and K1 has the potential for amazing discoveries. Some models predict a sharp outburst or even fragmentation as solar heating increases. The risk is real. Comets on such dense orbits often break apart, and predicting the exact time or outcome is impossible. Meanwhile, the community was divided in opinion on how quickly data should be published and who should receive credit for the discovery. The initial delay of the Small Planet Center in publishing the orbital elements of K and the subsequent disputes over naming rights revealed a tension between the desire for quick transparency and thorough verification. As the end of the year approaches, K remains a wild card both in the sky and in the astronomical community. The comet's tail is not just a stream of gas and dust, it is a moving laboratory for plasma physics. When sunlight heats the core of a comet, the ice sublimates and releases both neutral particles and dust grains. Some of these grains become electrically charged, while gases are ionized by ultraviolet light. As soon as the particles are charged, they are captured by the solar wind, a constant stream of plasma and magnetic fields from the sun. Here, the Lorentz force begins to act. Charged particles and ions spiral and accelerate along the lines of the magnetic field, forming a comet's tail in real time. As a result, the tail can bend, break, or even completely detach when the magnetic environment changes. Inside the tail, double layers form, areas where positive and negative charges separate, creating local electric fields. These structures can persist for hours or even days, maintaining clear boundaries or sharp breaks that observers sometimes note as disconnections or sudden changes in brightness. Since dust grains are heavier than ions, They react more slowly and often lag behind, tracing arcs and spirals as the tail evolves. This separation explains why comets can simultaneously display both a straight bluish ion tail and a broader curved dust tail. Understanding the effects of dusty plasma is key to interpreting comet images. Rapid changes in the tail, sharp breaks, or unusual morphologies are not just coincidences. They are imprints of the interaction between charged particles and the changing magnetic fields of the solar wind. For those who observe the sky or study telescope data, these patterns are fingerprints of plasma physics in action, unfolding millions of kilometers from Earth. A unique season of comets like this requires more than just sideline observation. Courtyard telescopes, remote observatories, and even binoculars become tools for real science, not just personal enjoyment. The International Asteroid Warning Network calls for coordinated observations as comet Tri-I Atlas prepares to reappear after its conjunction with the Sun. They request to provide sequential time images and accurate photometry, especially in the weeks after the end of November. For the Lemmon comet, rapid changes in the structure of its jets mean that even brief observation sessions can capture something new. Astronomy enthusiasts capable of recording sequences and processing them with open-source software help track the gradual evolution that larger observatories might miss. While the International Asteroid Warning Network bulletins highlight priority targets and inform the community about sudden bursts or comet tail shutdowns, patience and technique yield results for observations near the Sun. Separate frames are noisy and unreliable, but layered exposures reveal structure and movement. One should avoid chasing viral headlines or unverified statements. The most reliable information comes from processed images, verified reports, and data shared by the community. Every observation, no matter how insignificant it may seem, can influence scientific history. Whether it's spending time with the streams of Lemmon, measuring the fading arch of SWAN, or helping to track the path of the 3AI Atlas, your data becomes part of global efforts. This is the season when amateur astronomers work side by side with professionals, and the next breakthrough could come from any backyard or remote telescope. As comets brighten and fade, the window for discoveries is open, but not for long. In the year 2025, the inner part of the solar system will be visited by one interstellar object, 3I Atlas, and 3 large comets, all reaching perihelion within just 4 months. This rare alignment, recorded in international surveys and public campaigns, provides an unprecedented view of comet dynamics and interaction with sunlight. The Tenerife campaign showed how the double streams of Lemmon change in real time, while the threat of 3LY Atlas hides behind the Sun, waiting for further analysis of its true structure and origin after November. Some questions remain open. The precise inclinations of orbits, the risk of fragmentation for K1 Atlas, and the full impact of recent solar flares on the structure of comets. Nevertheless, the evidence confirms the scientific value of the current season and the importance of coordinated observations. As files and images continue to arrive, the comet season of 2025 serves as a reminder. When rare objects converge, swift cooperation and open data transform our understanding of the solar system.